Hey girls, there are just a few things that I wanted to show you in chapter 19 to assist you in your reading. So if you could follow along with me on page 363, you should have already read about the fact that the to and fro vibratory motion of the swinging pendulum traces a curve, special curve known as a sine curve, and then in the picture on page 364 you see Frank Oppenheimer showing how a pendulum traces a sine curve. So here's a video which illustrates it, I think, a little bit better than a static picture. The pendulum, simple pendulum, goes up and down, and as the conveyor belt moves underneath it, it traces this curve known as a sine curve. You're probably familiar with the sine function. And if you graph the sine function, sine of x, then it will give us this picture, this curve. So this is a very important curve in physics. So to illustrate this, I'm going to show you this wave on a string. So there are certain things about a wave that you might remember from previous science classes. One is that waves have an amplitude. That's the highest that they go. So if I pause it, I can measure the amplitude here. It's from the middle line to the topmost part of the wave. So you can see that this wave has an amplitude of about 0.5 centimeters, and you can see that here that's what I've set it to. So I can set the amplitude to be twice as big as that at 1 centimeter. And you can see that the amplitude now measures as 1 centimeter. Okay, good. You can also adjust the frequency of a wave. So every wave has a frequency which tells you how many times per second the wave vibrates up and down. So you can see that if I set the frequency here to be very small, right here, maybe 0.1 hertz, this dot is moving around this circle and the piston is going up and down, moving these beads. It takes 10 seconds for it to go around once. And here, if I increase with the frequency, now the frequency is 3 hertz. This circle goes around 3 times per second and creates a wave in which the crests are much closer together. So you may remember that the distance from crest to crest is called a wavelength, right? So here I'm measuring the distance between these two crests, and it's a little bit more than 2 centimeters, maybe 2.1 centimeters would be the wavelength of this wave, okay? And then notice that when I adjust the frequency here down to 1 hertz or 1 vibration per second, the distance between my crests, or the wavelength, is like a whole lot more. It's from here to here, looks like it's about 6 centimeters. So you can see that the frequency and the wavelength are connected. All right. So that's explaining the graphic on page 9, or figure 19.3. Something else that I wanted to point out is that even though it looks like the wave is moving, and I'm going to put this in slow motion, you'll notice that each bead is only moving straight up and down. So like keep your eye on the green beads and you can see that it just moves in a straight line up and down. So even though the crest of the wave is traveling along here, and you can measure that speed, and that's known as the wave speed, which is discussed on page 366, each bead only moves up and down. Skipping a little bit over to page 369, interference, I want you to look at the bottom of the page, and you can see that figure 11 or 19.11 is a picture of constructive interference versus destructive interference. Constructive interference is where you have two waves which are added together to make one wave which amplitude is twice as big. And then destructive interference is an example, is a picture there you can see that one wave is going up when the other one's going down, and it's going down when the other one is going up. And so in effect these two cancel each other out and you're left with no wave. So I'll show you that here. You can see that when I pulse this, oops, sorry. I'm going to fix this end so that the wave reflects back on itself, okay? So when I pulse this, the wave reflects back at the fixed end and comes back to the starting point and reflects again, and then travels underneath again. So what happens if I pulse it again right when it's reaching the starting point? So I'm going to pulse again. Well, that made it wider. Let me see if I can make it taller. No, it's just 3 times as wide. Okay, so you can see that when I pulse it, it just sort of keeps adding to the height of the wave there. There, I did it. Now I'm going to restart it and do the same thing again. And I want you to see what happens when I send another wave just as the other one is reflecting. Notice how when the two waves meet each other in the middle, it becomes like a straight line and they cancel each other out right there. Well, right before there. Like that. So that's the idea behind wave interference. Two waves can interfere to cancel each other out. Okay, the last topic that I want to discuss with you right now is the idea of standing waves. So I'm going to set this to oscillate automatically with a fixed end. So first I just wanted to, there we go, okay. So I'm going to set the amplitude here to be very small, like 0.05 centimeters. And I'm going to set the frequency to be 0.4 hertz. And I'm going to take it out of slow motion. Okay. And I want you to notice how this wave doesn't really seem to travel very much. Each one goes up and down, but the crest stays in the same spot, right there in the middle. Okay. Now I want you to see what happens when I double the frequency. The frequency is now 0.4, but I'm going to make it 0.8 hertz. There we go. I'm going to hit the restart button so you can really see what happens. Notice that now I've got two crests going on, one over here and one over here. And this green dot right in the middle here is what's known as a node. So when the wave is moving, this node in the middle really kind of stays in the same spot. And that only happens at certain frequencies. So that's why I was so careful as to pick my frequency. So you've probably encountered this when you're playing with jump ropes. You know that you can get a standing wave if both you and the person on the other end are vibrating your hands at the same frequency, and you get an arc and the crest doesn't move, and enabling people to jump through it. If you both vibrate your hands twice as fast, then you can probably get a standing wave with a frequency which will enable you to have like a standing node in the middle. And now watch what happens when I triple the frequency to 0.2 hertz or thereabouts, and I'm going to pause it and restart it again. And you should see 3 crests. Yeah. 1, 2, 3. And then these 2 green dots are the nodes, which stay in one spot. And these places where the wave is cresting is called the antinode. All right, so that's kind of all I have right now. Make sure you send me your questions on the reading, and we will discuss it all on Friday.